Almost all waves require a material or a medium to travel in. These types of waves are called mechanical waves. Examples of these mechanical waves include waves you see on the surface of water. Another would be the sound waves that are transferring information from your speaker through the air to your eardrum. Sound waves can also travel through solids and liquids. And in fact, they can propagate through denser materials much faster. So let's say we have two mechanical waves, a water wave and a sound wave. And this sound wave is travelling through a metal bar, for example. What would you say is the medium for both these waves? So with a water wave, the medium is the water itself, or the molecules of water. And for the sound wave, when it's travelling through a piece of metal, the medium is whatever the metal is made up of. So a mechanical wave requires a medium in order to travel. So if we place a speaker in the vacuum of space, or any other vacuum, the vibrations from the speaker won't travel anywhere because there's no medium for the waves to travel in. So do any waves exist that don't require a medium to travel in? So we can have waves like electromagnetic waves, which range from radio waves, microwaves, visible lights, ultraviolet, and X-rays. Without these waves, we would not receive any light from the sun, and our sky would look completely black. So if we go back to mechanical waves, when mechanical waves travel through a medium, it's important to realise that the atoms that make up that medium do not get carried along with that wave. So when a wave travels from one end of a medium, say a metal bar for example, to the other end, what these atoms do within this metal bar is oscillate about some fixed position. So if we have a look at this online example from the PhET website, and I've got a link in the description or in the comments below if you want to try this out yourself. In this example, we've got a couple of red dots or a couple of coloured dots along the length of this rope. You'll see that when we send a pulse wave through this rope, or in other words, when we shake this rope up and down only one time, a wave will travel from your hand or from the motor to the end of the rope. So we have a mechanical wave here travelling through a medium made up of this rope, or these circles here. But these green spots here will not follow the wave. It will simply oscillate up and down in a vertical position, so long as there is a wave travelling through. And this motion is perpendicular to the wave motion. In other words, the medium is moving at 90 degrees to the motion of the wave. And we call this type of wave a transverse wave. Now, with our rope example, if we now continue to make pulses with a steady rhythm, you generate a periodic wave. And you'll see this wave travelling along the rope towards infinity. So let's draw this periodic wave on a graph. And we have the displacement of the medium along the y-axis. This shows us how far the rope is moving up and down. And along the x-axis is the distance the wave has moved down the rope. So this periodic wave is a transverse wave because the particles that make up the medium will vibrate at right angles to the direction of the wave. And we saw this with the green particles. We also call this type of wave a sine wave because we can plot this wave using the trigonometric function y is equal to sine x. And just to be clear, this represents a periodic wave at a specific snapshot in time, almost like we've taken a photograph. So each periodic wave has a number of important parts to it. We have the crest of a wave, and the crest is the highest point above the equilibrium position. And the equilibrium position lies on the x-axis, where the displacement is equal to 0. We also have the trough of a wave, which is the lowest point below the equilibrium position. The amplitude of a sine wave is the distance from the equilibrium position to a crest or a trough. And the wavelength is the distance along the x-axis between two troughs, two crests, or the distance between two adjacent similar points on a wave. And let me draw this here quickly. So this type of wave is a transverse wave, where the medium's particles move at 90 degrees to the motion of the wave. But transverse waves cannot model how sound waves travel through the air. Sound waves are a type of wave called a longitudinal wave. Longitudinal wave is a wave whose particles vibrate in the same direction as the motion of the wave. So they vibrate in parallel to the wave motion. And we can see this with another website we have here. And I've put a link in the description so you can read up more about this. So in this example, we've got lots of circles here that represent atoms of a gas. And as a pressure wave moves through this medium, which is made up of these monatomic gas particles, we see that the displacement of these gas particles move in the same direction as the motion of the wave. But notice, again, that these gas particles, they don't follow the wave motion. They move back and forth about some equilibrium position. You also notice here that the gas molecules will compress and expand depending on whether the wave is at a crest or a trough. So if we're at the crest of a wave, the molecules will bunch up together. If we're at the trough of a wave, all the molecules move apart. Now, the longitudinal wave can also be described by a sine curve, but the y-axis now represents the density of the particles and not their displacement. So again, the sine graph here represents a snapshot in time as the wave is travelling through the gas here. So at A, the gas molecules are densely packed together at some peak density at the crest. As we move further right on this sine curve, we see that the gas molecules move apart until it reaches its equilibrium state at point B. And this is what the gas molecules would look like if there were no waves travelling through. So, for example, if they were in their relaxed position. Then as we move down to point C, the gas molecules have spread out as far as they can for this particular wave. So this type of wave, represented by the sine graph here, is sometimes called a pressure or density wave. So how does this longitudinal wave work as sound in air? So we're going to come back to the PhET website now, and I'm going to show you a different type of app, and I want you to think about what is happening to the gas molecules here as the sound wave travels through. Well, again, the air molecules are going to squish together at high density regions and will move apart at low density regions as the wave is travelling through. And again, we can play around with the amplitude and the frequency on this site to see how this affects how far these gas molecules move back and forth. So how does the period, frequency and speed of a wave relate to one another? The frequency of a wave describes the number of wavelengths that pass a given point in a unit of time. If we think about the keys on a piano, for example, on the left-hand side, we would have the low frequency notes, and by hitting one of these keys, the piano will send out a longitudinal wave into the air at a frequency of around 30 Hz. This means that one full wavelength of sound from this piano is hitting your eardrum at 30 times per second. The highest note on this piano is around 4000 Hz. And again, this means that the sound is vibrating your eardrum at 4000 times per second. The period of a wave is the time it takes for one complete cycle of vibration, or one complete wavelength to pass a given point. and we measure this in seconds. Now, to measure the speed of a wave, either a transverse or a longitudinal wave, we can use one of two formulas. So the first formula is the speed of the wave, v, is equal to the frequency multiplied by the wavelength. Or we can find the speed of a wave by dividing its wavelength by its period. When we look at any mechanical waves moving through a medium, the speed of the wave remains constant, even when the frequency and the wavelength change. And this is because the speed of the wave depends upon the properties of the material. So for example, any sound wave at sea level and at 20 degrees Celsius or about 70 degrees Fahrenheit, all these sound waves are going to travel at the same speed, which is about 340 meters per second. If we change the properties of the material, for example increasing the temperature or lowering the pressure or increasing the pressure, it's going to affect how fast the sound waves travel through the air. So if we have a look at the PhET app, we can see all the air particles here jiggling around randomly. We don't have any sound waves travelling through this medium at the moment. If we lower the frequency, if we send a sound wave through with a low frequency and send a pulse wave through, we can see the wavelength is quite large. But if we now increase the frequency of this wave, the wavelength shrinks. But what you notice here, if we time both waves, is the speed of the wave stays the same. So if we have a look at our formula, the velocity is equal to the frequency multiplied by the wavelength. If the velocity cannot change, then when we modify the frequency or the wavelength, the other variable must change in response to ensure that the velocity remains constant. So if we increase the frequency, for example, this would mean we need to reduce the wavelength. If we decrease the frequency, then the wavelength will increase. And we can see this here in this simulation.